My name is Mr. Akinwale Rotimi. So, I'm here to take you DPH 201, which is symptoms phase 211, and the course title is Introduction to Earth Physics. Introduction to Earth Physics. Now, what we're going to have in this course, this is a synopsis of the course. We have the Earth's history, the Earth's interior, seismicity and earth zones, the nature of the gravity field of the Earth, the measurement of the gravity and the figure of the Earth, the Earth's magnetic field, rock magnetism, polar warming and the continental drift, heat flow and geothermometry. But in order to make you understand better, I need to follow a particular flow that will make it easier for you. So the flow with which we are going to take this course is what we have listed here. We are first going to talk about the Earth's history. Before we go to the Earth's interior, what we have in the interior of the Earth. The Earth's history is about how was the Earth formed, what is the best hypothesis or story that we can give a logical reasoning of how the Earth was formed. Then we have what we have inside the Earth, in the interior of the Earth. Then we now move to polar wandering and the continental drift. We are going to talk about rock magnetism, of which we have to talk about the magnetic field of the Earth. Of course, earthquake zones and seismicity. Why do we have earthquake occurring in some places? And what are the relevant properties that we need to look at? Now, we talk about, after that, we move to the nature of the gravity field of the Earth, the measurement of the gravity, and we talk about heat flow and geothermometry. Who can tell me what do you mean by geothermometry? Geothermometry.
This should be the study of, because beneath the Earth's subsurface there's an energy, that is heat energy, that's the subsurface is generating. That's it. We take advantage of it, like we use it for our daily, just like using the energy, heat energy for.
Okay. Now, in summary, when you look at the term geo means the Earth. Therm is about thermometer. Thermometry. So we're talking about the heat of the Earth. So the heat of the Earth, that's geothermometry. Where geo represents the Earth, thermometry means the heat itself. Okay. Now, to start with, let's start with the Earth history. Let's look at the solar system. We have the Sun here. We have the Mercury, Venus, Earth, Mars, and we have what we call the asteroid belt. We have the Jupiter, we have Saturn, Uranus, Neptune, and what we have the Kuiper belt objects. So let's look at this clearly. We can notice that each of these planets are small, while these ones are very large. We have an asteroid belt, and each of these planets, they don't have asteroid close to them. It's like they've cleared them away from their neighborhood. Okay. Then we have the Sun being the largest object. And one thing we also notice is that these ones are very dense. The ones close to the Sun have high density, but they are very small. The big planets have low density, but they are far away. So what can we say about that? We are going to look into the history of the Earth. Having look at that, what properties make a planet? What are the properties that make a planet? For any object to be a planet, it must orbit around a star, such as the Sun. You know, the Earth is orbiting around the Sun. Now, a moon is not a planet. Why is it not a planet? Because it's not orbiting around the Sun. It's orbiting around the Earth. So when it orbits around the Earth makes it, it follows the Earth around the Sun. So it's not doing that on its own. So we don't consider it as a planet. Okay? But we consider it as a satellite. It's a satellite of the Earth. Just like you send out satellites there, they also orbit around the Earth, they move around us, and they send us signals and information from wherever you wanted them to send it. Okay? Now, it must be large enough so that it has a gravitational, so that the gravitation results in a spherical shape. Okay? That is, it's so large that because it is spinning around, it now looks like a circle, like a ball. Okay? Now, another thing that it must not be so large to initiate nuclear fusion. Remember that in your year one, you are taught nuclear reactions in which we have nuclear fission and nuclear fusion. In fusion, we have the combination of small nuclei to form a larger nucleus. For instance, hydrogen to form helium. So the sun is generating the heat from that process. The Earth is not generating the heat per se. No, it's not burning. So none of the planets are burning. It's only the stars that burn. Sun is an example of a star. So it burns due to that reaction. Now, the third thing is that it must be large as we initiate, it must not be so large. Then the fourth is, it must have cleared the neighbor around it of planetesimals. What do we call planetesimals? They are like dwarf planets, small planets. Okay, now if we go back to that image again, we can see that these small objects, they are all cleared away from the neighborhood of this planet. That's what makes them planet. We won't see all these several objects playing around each of these. The same thing applies to Jupiter and the rest. You see that they are not playing around that neighborhood. Okay? So going back to that, let's look at the conditions. Conditions 1 and 3 are met by all objects orbiting the Sun. What we mean is that the condition 1, we have all these asteroids, they also orbit around the Sun. They also, most of them are circular in shape. Okay? But that doesn't make them a planet. Now, 1 and 2, and it's not a satellite, it's called a dwarf planet. So if you have 1 and 2 and it's not a satellite, then it's a dwarf planet. For instance, the Pluto is not really a planet, it's a dwarf planet. Okay? It's very small. Okay? We also have Ceres and Eris. You can see that Ceres didn't clear its neighbor. This is Ceres. It didn't clear its neighbor of all these particles. Okay, so it is not a planet. Because it must have enough gravitation, is to either pull them so that they will move around it, or they should move away from it. Okay. And just like the image. Now let's look at the Earth as a planet. The Earth itself as a planet. Now, we know that the Earth moves around the Sun in a slightly elliptical orbit. What do we mean by slightly elliptical orbit? We can see that the Earth is tilted and is moving around. It's not in a circular form, but in an elliptical form. Remember the Kepler's law in year 1? Kepler proposed that the Sun is at one focus of the ellipse. The other focus is empty, and the Earth goes round. So in an ellipse, what happens? When you're on the farther side, it will be different from when you are on the closer side. So at a point, you'll be close to the focus of the Sun. At another point, you'll be far away from the Sun. So we're going to look at the consequences of all these processes. Now, we know that the Earth rotates about its own axis from one solar zenith to the next one, and that defines a day. What we mean is that when the Earth rotates about that axis, we have both day and night. Right now, we're in the morning because the Earth is rotating us to face the Sun gradually. By noon, we will be facing the Sun directly. By noon to 1 o'clock, that's why the Sun is very hot during that time. So by the time it is midnight, you are already back in the Sun. Then that's why it will be day somewhere else. Like in America, it will be day in America, because by that time, the Sun would have turned America to face the Sun. Okay? By the time it is 11 p.m. here, it's just 5 o'clock in the evening over there. Okay? So, and that's how it rolls. Okay? Now, and that's why you notice that some people are ahead of you in time. Because the Sun is going to turn, the Earth is going to turn them to the Sun at different times. Okay? Now, what makes a year? The length of time taken for it to complete one orbital revolution. You can see that from autumn, I'm still going to bring it back to our weather. Okay, from autumn, it moves to winter, spring, and summer. You see, it's moving around. So the reason why we have seasons is because of the Earth rotates around. It's moving in that elliptical order. Day and night is when it moves around its axis. Okay, weather and seasons is when it goes around the Earth. For instance, when you have winter, that means that it is far away from the Sun. The other is close to the other focus that is empty. Okay? So what happens? It will be very cold over there. And here too, we have what we call this harmattan. And the harmattan is usually very cold. temperature can drop to as low as 20 degrees Celsius during the harmattan. So it's because the sun is far away, I mean the earth is far away from the sun. Now, during the summer over there, that means that at that time they are close to the focus. So anyway will be warm, the weather will change, and it goes that way. Okay? Now, the eccentricity of the orbit is like 0.167. That is how the eccentricity is just about eccentricity of an orbit is when you look at radius of the first focus and the radius of the second focus and you divide it, so you get something like the eccentricity. Now, we also have the mean radius of the orbit. It's about 149,597,871. Okay, that is very large, right? Because the diameter of the Earth itself is just 6,400 kilometers. Okay, and distance within the solar system are usually expressed as the multiple of this unit. So we call it astronomical unit. So if I tell you that the astronomical unit, when you look at the distance between the Mercury can be like 1/4 of this AU, while Venus can be like half of it. Then when you talk of Mars, it can be like twice of it. That's God's law. Okay. Now let's look at the distance. We call the distance to extragalactic celestial bodies. They are expressed as multiples of years. What do we mean by galactic bodies? We are talking about looking at other solar system. I mean other galaxies. We are in the Milky Way galaxy. So galaxy is a collection of stars. So if I want to look at those stars, it takes several years before the light of those stars gets to us. It's interesting to find out that the sun's light takes about 8 to 20 minutes to get to the Earth. That's 8 to 20 minutes. So this light you are seeing left the sun 8 minutes 20 seconds ago. Okay, it left the sun. So if you snap the picture of the sun now, you are snapping the picture of 8 minutes 20 seconds ago. Okay. Now, looking at that, we have other properties such as the gravitational constant mass, which is 5.97 times 10 to the power 24. We have the gravitational eccentricity of about 0.986, or now this is similar to the gravitational constant that we have 9.8. There's a way you compare this mass and this, then you come up with that. Now the axis is inclined at 23.439 degrees. Actually, if you look at the history behind this inclination, was when the moon was formed from the Earth. When there was a great impact on the Earth, then the moon was cut off, and at the end of the day, the Earth got tilted by that angle. So presently, it's about 23 degrees. 23 degrees tilt. Now, the origin of the solar system. If we want to define the solar system, if we want to talk about the solar system, okay, we must be able to meet up with some theories that we have there. But one thing we know is that the origin of the solar system is about 4.5 to 4.6 billion years. This solar system is about 4.5 to 4.6 billion years. What do we mean? How do we know? We have some meteorites. Meteorites are stones that fly around in the space, and some of them will get attracted by the gravitational pull of the Earth, and they find themselves in the Earth. Because we know that those stones have not been altered like one we have here. You know, we have several alterations here. Today you can have igneous rock. That igneous rock will change to metamorphic, from metamorphic change to sedimentary rocks. But think about a rock that have not been altered. Okay, a meteorite. So doing your dating on it, we found that it's about 4.5 to 4.6 billion years. So these rocks must have been part of the solar system when it was formed. Okay, so looking at that, a successful theory or story should tell us the following observation or the following properties. Because we notice that except for Pluto, the planetary bodies lie in or close to the same plane which contains the sun and the orbit of the Earth. We call this the ecliptic plane. What do we mean by the ecliptic plane? For instance, let's say this is the sun. Okay, if this is the sun, this Mars. If Mars is here, I mean if Mercury is here, Venus is here, Venus is not here, Venus is not here, it's here. They are formed like a straight line. We have the Earth on that same straight line, and so you can see that it's formed like a flat disk. Not that you have Mars up here, you have Earth down here, then you go and have another one down there or another one up there. No, they are like on the same plane, and they keep rotating around the sun. Okay, looking at that, we notice that they form that's what I call the ecliptic plane, that flat plane, that they are all arranged. There is no rope tying them, there is nothing holding them, but they move in that plane. Okay, we also notice that they revolve about the sun in the same sense, which is counterclockwise. They move anti-clockwise around the sun. Most of them move anti-clockwise. So if Mercury is moving this way, Earth is also moving this way. Okay, Mars is also moving this way. Why? You know, we are looking at anything you are going to tell me that caused this thing to be, it must be able to explain all that. Okay? Now, besides that, we notice that except for Venus that move in the retrograde direction, Uranus and some other few ones,